Okay, good morning all. Am I audible, sir?
Yes, you are audible.
Okay. So once again, on behalf of Shipshankar Technical Campus, I welcome you all in this auspicious short-term training program. So today we are having with us one of the most eminent personality in this teaching field and in the research field, Dr. Shipshankar Mahapatra, sir. He is presently professor in Mechanical Engineering Department in NIT Rourkela. So let me introduce a bit about him. So his area of interest are generally the manufacturing processes, the production techniques, optimization of processes, quality control, etc. and lot many. So this time is very less for briefing him, though I am trying my level best. So he has previously has completed his BTech in Mechanical Engineering from Sambalpur University, followed by MTech in Production Engineering from REC Rourkela, which is now known as NIT Rourkela. Then sir has completed his PhD in 1999 from IIT Kharagpur in studies on some aspects of just-in-time implementation in Indian manufacturing organizations. Professor Mahapatra has guided 9 PhD scholars and helping them in their research work for completing their research work, and presently he is guiding 11 scholars under him. And sir has membership of 6 professional bodies like Institute of Engineers, Indian Society of Technical Education, etc. Professor Mahapatra has 129 publications in reputed international journals, 23 papers accepted in the international journals yet now, and 28 publications in reputed national journals, 163 publications in international conferences, 61 publications in national conferences. Apart from this, sir has 5 book chapters, 5 sponsored projects as PI and 1 as co-PI. 3 projects has already been submitted under various allied organizations like DRDO, MHRD, DST, CSIR, and lot more. Sir has completed 3 consultancy projects for IFGL Refractories Limited, Kalinga, Odisha. Sir has conducted various self-financed education programs for creating educational awareness, knowledge, upgradation, etc. He has done all this enhancement in his lucrative career though he is having enormous amount of administrative responsibilities upon him. He is very renowned personality in education and research field, because of which sir has received many national and international awards. In 2009 and 2012, sir has been appointed as visiting faculty to Industrial Systems Engineering, School of Engineering and Technology, Asian Institute of Technology, Bangkok. He has been also exposed to global scenario because he has visited many countries for delivering his sessions in many national and international conferences. Some other very important contribution of sir to the society as well, like he is reviewer of many international journals for last 10 years. He is editorial board member of many journals. He has chaired many conference sessions. He has also examined many PhD theses. He is member of many advisory technical committee of conferences. He has total 745 citations in Scopus and 665 citations in Google Scholar so far. Sir is also having 3 patents and design registrations, which are ultra portable washing machine, gravity flow portable water bottle with filtration system, and design registration applied for portable water bottles. So this is, I have tried this brief introduction about sir. Now I welcome sir for delivering his eminent sessions, which will be very useful for us. Please, sir.
Thanks, Professor Burma, for a nice introduction. But the data was a little bit old, and I don't know where you have collected, but it is a little bit old. Anyway, I'm really happy to interact with you related to optimization techniques and mostly applied to manufacturing field. I shall be mostly concentrating on the latest optimization techniques. That is latest optimization techniques like simple optimization techniques, SOPT, then harmony search algorithms, all are nature inspired algorithms. Uh, Please mute your microphones. So these algorithms I shall be discussing, and I shall give you how to apply these algorithms in actual manufacturing field, as well as I shall demonstrate how to run the code in the MATLAB platform. Um, so, although I have been assigned to discuss only the SOPT and harmony search algorithm, I shall be covering little bit more of algorithms. It is the constant, on-constant, and multi-objective optimization problems. Um, is the slide visible to everybody? Hello? Can you see the slide?
Yes, sir. Yes, sir.
Yes, sir. So, mostly the topic that I shall be discussing is application of meta-heuristic methods to manufacturing problems and its research scope with case study. Um, Before going to the actual topic, I shall give a brief introduction. What do we mean by optimization problem? In any optimization problem, we are intended to find out what is the best possible values. Best possible values. So you will be given an fitness function or the function which is being optimized. This function is we can call y is fx. So this is the optimization function. X is a vector of variables we call design variables. So now this is minimized or and x is a vector of design variables. It will have x1, x2, x3, x4 like this. So x is defined as a vector, as a column vector, and subject to some constraints. Constraint there may be um, inequality constraints, m number of inequality constant, and maybe equality constant. So Gix is less than equal to 0, that is the inequality constant, and Hx is equal to 0, that is the equality constant. And all the variables x, x2, x3, all these variables will be within some bounds, within the lower and upper limit. For example, I am to find out the maximum material removal rate in a turning process. One steel bar is turned with HSS steel. My objective is to find out the maximum material removal rate. Now, material removal rate, that is a function of some process variables. Process variables, I mean the feed, depth of cut, and the speed, cutting speed. So we should have some functional relationship between y and these variables. X1 maybe the cutting speed, x2 maybe the depth of cut, x3 maybe the feed. So we should have y, which is material removal rate, is a function of these variables, and so we should have a functional relationship. This functional relationship can be obtained either through analytical method using the physics or the principles of physics, or we can get it using the numerical methods like finite element method, or we can get it a relationship between y and x. That relationship, mapping of this relationship, we map x with y. This relationship we can get using some empirical relation. Empirical relation I mean we conduct the experiments and get a regression model. The regression model may be linear regression or maybe non-linear regression. So, but any functional form which suits to the problem that we should get. Now, this function is to be optimized subjected to some constraints. If there is no constraint existing, then we call it unconstrained optimization problem. If the constraints are existing, then we call it a constraint optimization problems. So this is the basic format of any optimization problem. Now, now sometimes what happens, you may have more than one objective to be satisfied. For example, again I shall take the example of the turning process. In the turning process, we want that material removal rate to be maximized. At the same time, surface finish is to be surface roughness is to be minimized. Surface roughness on the machine surface, average surface roughness on the machine surface, that is to be minimized. So these are two contradictory objectives. These objectives are simultaneously satisfied at what condition or what parameter setting of speed, feed and depth of cut that you are interested to find out. Now in that case, since we are having two objectives, both the objectives need to be satisfied. In that case, we call it a multi-objective optimization problem. As usual, in the multi-objective optimization problem, we will have functions y, the function relation y and x. What is the functional relation? We can keep this y as a vector, that is f1x, f2x, fqx, if q number of objectives are to be simultaneously satisfied. Now f1x may be the maximization of material removal rate, f2x may be the minimization of the surface roughness. So multiple objectives are to be satisfied simultaneously. That is the case when we call a multi-objective optimization problem. In multi-objective optimization problem, it is difficult to get a single solution unless you convert the multiple objective into a single objective using some weighted function. Then you cannot have a single solution. Rather, we will have a set of solutions which we call Pareto solutions, or these are the non-dominated solution. Later on I shall discuss what is the Pareto solution, but you will get a set of solution. Out of the set of the solution, you have to select the best one. Now, it may so happen that in multi-objective optimization case, either all the objectives are to be maximized or all the objectives are to be minimized, or some of the objectives are to be maximized and some to be minimized. Whatever may be the case, any maximization function can be converted to an equivalent minimization function if you multiply the function by -1. Okay, maximization fx is same as minimization of -fx. So any function can be converted to maximization and minimization simply by multiplying by -1 or taking the reciprocal of the function. Say maximization of fx is equal to the minimization of 1 by fx. So this is the way we do, and we do it only because if all the functions are maximization or minimization type, then it is good. It is easy to solve such type of problems in multi-objective optimization case. So these are the constants that we find in the multi-objective optimization case. Now the question is, we have to find out the optimization means finding out the best values of decision variables x1, x2, x3, so that either fx is to be maximized or minimized. To solve such type of problems, we have traditional methods as well as non-traditional methods. Now, in the traditional method, we have got direct search methods like regional elimination method, interval halving method. In the regional elimination method, you go on searching the best value, and where you do not, the region where you do not find the best value, we reject that region, so that region will be narrowed down till you get the best values. So basically, what we are doing in the optimization landscape, we are searching the best point. We are searching the best point. Now, now we search in a region. If you do not find the solution in that region, you reject that region and go to the next region. And that way, the search region gets narrower. One iteration by one iteration, the search space gets narrowed down until we get the best values. So this is the direct search method. There are indirect search methods where we, in the process of searching the best solution, uh, a single point solution, now we go on moving through the optimization landscape till you get a slope. If you get a slope for the minimation point, then we go on searching in that way. So that slope is very important. We get a slope to get the minimum values. If the objective is to minimization, so we want to find the a global minimum. We go on searching that, go on finding the slope. As long as you get the slope, then we get the we go on searching. So this is the indirect search method. Some of the examples are Newton-Raphson method, bisection method. These are the slope-based methods, or the gradient-based methods. So as long as you find the gradient, you go on searching till you get the best values. All these traditional methods are existing and well presented in the books, but still then we always search for good solutions and better algorithms for solving the optimization problems. The reason is very simple. If you use the traditional method, it may so happen that particularly in the gradient search methods, the gradient will be so small that your search will not take place, or the search is stopped at that point. We call it we are trapped at the, or the algorithm has trapped at the local optima. That a search is being stopped and we trapped at the we will be trapped at the local optima. So that's why these traditional methods are not general methods to solve the different types of objective functions that we have, and all the complex relationship that we get these days, particularly in manufacturing. So to avoid this, what we what we call we do a stochastic search. Instead of a single search, we do a stochastic search method, and in that method, these methods are known as non-traditional algorithms, or called also called evolutionary algorithms, also called meta-heuristics or nature-inspired algorithms. The reason is that most of these algorithms are inspired by nature. That's why these are called nature-inspired algorithms. These are called meta-heuristic. The reason is that it is just a heuristic means, literary meaning of heuristic is the computerized thumb rule. So it is the it is some way a thumb rule is used, a computerized thumb rule is used to search the algorithm. But these thumb rules or the heuristics are quite general. It can be adapted to any type of problem, or evolutionary algorithms, because it evolves solution one by one. So now look at here. You see, this is a function fx is given, which is a function of a design variable x. Now we have got local minima here, whereas the global minimum is here. Our objective should get it the global optimum. Now, if you use the traditional method, the slope that we get, the slope may be so small that once you reach at the local optima, it is very difficult to come over this. When we reach at this trough, it is very difficult to come over to this crest and get this or obtain this global optima. So this is the problem with the traditional optimization techniques. But the non-traditional methods, these are not a single point search, rather multi-point search techniques. From the multiple places, we go on searching the best values. And these are the stochastic methods. What you do, we generate solutions randomly, then evaluate for each solution, we evaluate the fx value or the fitness value, objective values, objective function values. Now, these 10, what we generated, this population or the 10 points randomly generated, that means we are searching from 10 points. Now, as per the algorithms method or the requirement of the algorithm, this initial solution is updated gradually until we get the best values. Now, I shall give a small example of classical optimization problem. We shall use a function called Rasterising function. This is a Rasterising function. Now, it is d is the dimension that I equal to 1 to d, which is a function of xi square plus 10 cos 2 pi xi plus 10. Now, this Rasterising function, we shall take only d equal to 2. In that case, you will have x1 square minus 10 cos 2 pi x1 plus 10 plus x2 square minus 10 cos 2 pi 2 plus 10. So, if you take dimension equal to 2, so you have got two variables, x1 and x2. If you plot this Rasterising function, then you find that it is a multimodal function. So many modes are there, and we will search in this region to find the best values. And the objective is to minimization. Now, the x1 and x2 will vary between two limits. So x1 varies between minus 5.12 to plus 5.12. Similarly, x2 varies from minus 5.12 to plus 5.12. Now, this value of this function fx will be equal to 0. That is the optimum value. Now, for solving such type of problems, if you go to the MATLAB, there is an optimization toolbox. You simply type optim tool, then the toolbox will come, and the optim toolbox, there are a lot of functions are available. You can use any function for solving the problem. But the objective function must be saved in a .m file, the objective function that we can write. So the objective function we have written we save the file as uobjfun.m. So this is the objective function written. That is the function fx uobjfun(x), and the function is given here. That is the x1 square minus 10 cos 2 pi x plus 10, then x2 square minus 10 cos 2 pi x2 plus 10. So this is the Rasterising function with 2 dimensions that is given, and that is written in a .m file that is known as eobjfun.m, and it is saved as the objective function file. Now you call, now you have to run this function. Either you use the MATLAB toolbox or you write this code that initially you have to give a guess of the solution. The guess is -1 to +1. Now these are the two commands that is to be used. Here you see the call for the FAMUN. You can see that is the function. The type of function that he will use, or the algorithm that he use, that is fmin unconstrained, that is the MATLAB function that he will use for solving this problem. Then when you use fmin, you will see the objective function is written here, or the objective function will be called. If you use the toolbox, simply you have to type at the rate the name of the file of the objective function. So automatically it can take, and this fmin unc can be selected from the drop down menu of the methods. So we can choose this. Now let us run this program in MATLAB. So it is solved now. You see the f value here. So the f value you got 0, and similarly the x values, that is 0, 0 for this Rasterising function. So this way you can solve the unconstrained traditional functions for solving many type of problems using the MATLAB's traditional optimization tools that is available, or the functions that is available. But these traditional optimization problems sometimes do not give good solutions to the complex problems. The reason being that the search will be trapped at the local optima, and it cannot come over the local optima, because if you use the gradient search method, the gradient will be very small. That is the reason we cannot get good solution if you use the such type of methods. That's why the stochastic methods, nature-inspired algorithms, or evolutionary algorithms, or meta-heuristics, these are frequently used these days to get the best solution. However, the optimum solution for a function is not, nobody has seen that what is the optimum value, but we think we may reach at near optimal solution and try to find out. Now, there is a classification of nature-inspired techniques. One is the evolutionary technique. Evolutionary techniques, mostly we use in the evolutionary techniques, that is the genetic algorithms. In the genetic algorithm, what we do, we generate randomly some solution. So that is known as a population pool. Randomly generate. Suppose y is a function of f, x1 and x2. So we randomly generate values of x1 and x2 and evaluate with fx and find out the value. Now, this from the randomly generated in genetic algorithm, we have three operators. That is the crossover operator. Then the first is the reproduction operator, crossover operator, and the mutation operator. So once a reproduction has been made, once the solution is randomly selected initially, later on it goes on changing. Now from that, we take two parents or the two solutions randomly and make crossover among them. Crossover is nothing but the exchanging of the information between these two. When you make the crossover, two offsprings will be generated. Now these offsprings may be superior to the parents or may not be superior. If they are superior to the parents, they will survive in the solution, and the worst solution from the worst solution in the solution pool or the population pool will be removed. So the offspring may be superior. So if it is superior, then it replaces the worst solution in the population pool. If it is not superior, then it will be rejected. So it is, if you imagine, it is the survival for the fittest. If a solution can survive, the offspring can survive if they are superior. The offspring cannot survive, it is worse than the existing solutions. So it is the case of the survival for the fittest, or what we call the Darwin's theory. In the Darwin's theory, it says the survival of the fittest, that is the theory of evolution. So the evolutionary techniques are genetic algorithms and other algorithms are existing. Similarly, there is another type of technique known as swarm intelligence techniques. In the swarm intelligence techniques, most important technique is the um, particle swarm optimization. In the particle swarm optimization, what you do, uh, you represent the solution by particles or the birds or the fish. It is based on the swarming of the birds or the uh, fish schooling. So the particle, we mean the solutions. So a particle can have any dimension, that is the depending on the number of decision variable you are having. Then randomly generate these particles having their position values. One is the position value and another is the velocity value. Now go on changing the velocity as the iteration proceeds. I shall give the demonstration later on. As the iteration proceeds till you get the best solution. So this is a swarm intelligence techniques. Similarly, physics based technique. The gravitational pull of different objects. This is a method of physics. So this method is used for develop the optimization algorithm. So it is based on the natural phenomenon. Similarly, human-related technique, the interaction among the human beings, that is inspired to develop the optimization algorithms. So one example is the teaching learning based algorithm, TLB. So these are the nature inspired algorithms can be divided into four types. One is the evolutionary techniques, that is the general algorithm developed by John Holland in 1960s, or differential solutions, differential evolution proposed by Stone and Price in 97. Then swarm, there are a lot of swarm intelligence techniques. Swarm intelligence techniques are artificial bee colony proposed by Karaboga, then particle swarm optimization proposed by Kennedy and Everhart, then artificial immune system proposed by De Castro and Juben, and moth flame optimization proposed by Mirza Lili, and firefly algorithm proposed by Yang, and Coco search algorithm proposed by Yang and Deb. So, in fact, if you go through the literature on nature-inspired algorithms, then you find a lot of swarm intelligence techniques. And recently, some of the techniques have been developed based on the physics. That is, the simulated annealing was existing, which is nothing but which is inspired from the annealing process of steel. What you do is, what is the annealing process? That is, we heat the object to a very high temperature to nearly towards the recrystalline temperature and gradually cool it down. That is what the annealing. Similarly, in a solution, you an artificial temperature is given and go on reducing the temperature, and some iteration will be processed as the temperature is gradually decreased till you get the best solution. This was proposed by Kirkpatrick and Gillette and Weichi. Then harmony search algorithm, which is based on the creation of the harmony, that is music. So based on that, It was proposed by Gim and Kim. Then gravitational search algorithm proposed by Rasedi et al. And water web optimization proposed by Jain. So then human related techniques, basically TLB algorithm proposed by Rao and Sapsani, Bakaria. So these are the different types of nature inspired techniques that we are having at now. Uh, Now, some of the nature inspired techniques that what we have discussed so far: genetic algorithm, differential evolution, simulated annealing, artificial bee colony. So I shall give some idea on say PSO, TLBO, and simple optimization algorithm, SOPT, and harmony search algorithm. So how these algorithms can be applied to solve manufacturing problems. Uh, so let us first discuss on simple optimization techniques. Simple optimization technique is recently developed, and it was developed by or proposed by Hassan Saivi and Azad in 2012. But very less work has been done in the done in SOPT. SOPT has a very important feature that it requires only one parameter to be tuned. If you go through the other algorithms like genetic algorithm, you have many parameters like population, size of the population, that is one parameter. Another is the mutation rate, then crossover rate, probability of crossover, probability of mutation. So there are so many parameters. These parameters are to be tuned. So if the number of parameters are more in any algorithm, then tuning this parameter takes a lot of time to get the good solution. So that's why if the parameters are less in any algorithm, then this can be tuned easily. So that's why SOPT is one such algorithm where we have got only one parameter. So if you tune one parameter, then the time required will be less and you can solve easily. So initially, what we do in the simple optimization algorithm, we generate a population or generate the number of solution. So this population will be fixed. It is not going to change from iteration to iteration. Only thing is that the worst solution will be replaced by if the solution is good, if the new solution is good. So the value of xi, design variable or parameter xi new value will be equal to best value. What is the, we have got the best values plus C1 and Ri. Ri is the a random number. Okay. And this Ri is a normally distributed random number with mean 0 and a standard deviation sigma I. Then similarly, again, another formula that we use is xi new, that is xi best plus C2 multiplied by Ri. C2 is known C2 is nothing but the half of C1. In fact, there is only one parameter. C1, whatever the value C1 you take, C2 will be half of that. So tuning will be very easy. Now the thing is, why do we use the two equations and two parameters, that is C1 and C2? The reason is that in any optimization technique, particularly nature inspired technique, there are two ways of there are two important activities that you do. That is, one is known as exploration and another is the exploitation. Exploration, we mean when you go on searching, when we are away from the optimum value, we give a bigger jump to reach at the best values. So that is the exploration, or giving a bigger jump while searching. Then exploitation is a finer search around or in the vicinity or in the neighborhood of the best point. So that first equation talks about the exploration and second equation talks about the exploitation. And R, R is the random, normally distributed random numbers with mean 0 and a standard deviation sigma I. Now suppose you have d number of variables, and this is the n number of solutions that we have generated, and this is the size of the size of the population size. This n is not to be going to change from iteration to iteration. Now, to use that equation, what we do here, for each variable, these variables are randomly generated initially. Now, for each variable in each column, we calculate sigma I. Sigma 1 calculated here, sigma 2, sigma 3, up to sigma d is to be calculated to be used in these equations, where I is a variable, counter for the variables. Now, you go on solving and getting the new solution. If the new solution is good, then it will replace the worst solution in the population. If it is not good, then it is rejected. So this process continues till we get the best values. Now it may so happen that your solution will not improve after some point of time. In that case, you may assume that your solution, you have been trapped at the local optima. To come over from that local optima, we can have a replacement counter that is given as 0.5 multiplied by the number of size of the population multiplied the number of variables. So after this number of iteration, or up to this number of iteration, if the solutions are not going to be changed, then you put some random solutions in the solution pool, or what you call, we put some variation in the solution. Since the diversity is lost in the solution, when the diversity will be lost, then you may not reach it, or you will be trapped at the local optima and you may not get at get the best values. So if you anticipate that you have been trapped in the local optima or the solution has lost the diversity, then artificially create some diversity. So to avoid that, what we do, a replacement counter is given. So after certain number of iterations, if the solutions are not going to be changed, then you artificially give a random solution to the solution pool, so that diversity can be found out, and then it will again further process. So what we if I so the main steps of SOPT, first you have to initialize the population, calculate the fitness of the population, sort the population based on fitness value, then that is to be then you have to repeat that, generate new solution by equation 1, then compare the worst solution of population with new one and replace if the new solution is better. Then they generate a new solution by equation 2, compare the worst solution of the population with new one and replace it if new solution is better. Now store the best solution found so far, replace best solution of the population if it remains best for limiting number of iteration. That's the replacement counter. What is the replacement counter I have shown? Then until this process, this repeating procedure will continue till the maximum number of iteration is reached. Now this is the flow chart given for SOPT algorithm. This is the flow chart. Now come to a small example where we can use this. Now again, we shall take a Rasterising function. I have given you the Rasterising function, how it looks like. This is the Rasterising function, and we shall assume again dimension equal to 2. So you will have two variables, x1 and x2, two variables that I have shown here. That is x1 square minus 10 cos 2 pi x plus 10 plus x2 square minus 10 cos 2 pi x2 plus 10. So initially randomly generate the solution. Take them. Now the values of x1 and x2 are within the limits, that is minus 5.12 plus 5.12. So within this range, you have to randomly generate the solution, x1 and x2 solutions, randomly generate within these two limits. So we can take the size of the population equal to 8. 1, 2, 3, 4, 5, 6, 7, 8. 8 is the size of the population. Now x1 and x2 values have been found out. The first randomly generated solution is for x1 is equal to minus 4.38, x2 equal to 4.96. Now we evaluate it. Fx function, it is 61.3899. Similarly, the second one we generated, and the fx is generate solution that put in that formula, Rasterising function, that formula, then you get a value of this. So all the 8 solution, the fx value has been found out. Now as per SOPT algorithm, for each variable we calculate the mean, and for x1 the mean is this, and the standard deviation is for the first variable 1.8821, for the second variable mean is 2.5463, and the standard deviation is 1.8543. So that we have found out. Now generate the random numbers. How do we generate the normal random numbers? How do we generate the normal random numbers? To generate the normal random numbers, first you generate random variates. Random variates can be generated. That is Z1 and Z2. Two formula are available. You can use any one formula. In fact, it was Z1. It is this is sine and this is cos. Okay, so you can use any one formula, either sine formula or the cos formula. Here it is wrongly written cos in both the formula. In fact, it is sine and it is cos. So you can use any formula. Now the normal random numbers Ri equal to mean plus sigma Zi. So now R1 and R2, whatever here use R1 and R2, these are two random numbers between 0 to 1. Now, now let us take Z1 that we found is 0.4781 for the first variable. Z2 we found that is 0.4153 for the second variable. So R1 will be mean, will be, you see the formula here, mean plus sigma 1 is 1.8821 sigma 1 multiplied by Z1, that is 0.4781, that is 0.8998. Similarly, R2 is mean is 0 plus sigma we got 1.8543 multiplied by Z2 0.4153, so it is 0.7701. So R1 and R2 we have found out. Once you find the R1 R2, then Xi new will be Xi best plus C1 Ri. So Xi new is the, so among these, which one is the best value? That is, this is the best value, which is giving the minimum fx value. So when x1 is minus 0.14 and x2 is 0.16, then fx is fx is 8.317. That is the best fx value. So now xi new will be x at best, that is minus 0.14, and C1 is 1.5 that we have taken. C1 is 1.5, R1 is 0.8998. So you got X1 new is 1.2097 or nearly 1.21. Similarly, X2 new will be, that is the 0.16. That this was the best previously also. So 0.16 plus C1 is 1.5 and R2 that we calculated R2 here is 0.7701. 0.7701. So it is 1.32. So two new solutions have been found out. Now these new solutions you evaluate with the function, and that is found to be 24.9774 fx value. When you put these new values in the fx function or the Rasterising function, so this will replace the worst solution. So what is the worst solution that we had previously? The worst solution was the first one, that is minus 4.38 plus then x2 equal to 4.96, 61.3899. So that will be replaced. You see, that was replaced with the new solution 1.21, 1.32, and the best solution, that is 24.9774. And then the best solution, it remains as it is. Now when you replace the worst solution with this new solution, because the new solution is superior to the previously existing the worst solution, now the next worst solution becomes this one, minus 4.60, 1.46, 61.0676. Then again we calculate the mean value for x1 and the standard deviation for x1, then mean value for x2 and the standard deviation for x2. Then find out randomly z1, z2, then r1 will be mu, that is the mean is 0 plus standard deviation, that is the 2.3242, 2.3242 multiplied by z1, 1.345. So it is
Sir, excuse me, sir.
Yes.
Sir, the mean is not 0, sir, but we are taking mean as 0.
Yes, so you use the mean is 0. That if you in the column, that mean will not be 0, but when you calculate for the we assume that mean is 0, but only the variation that is required for h. Mean is not required. We play with the variations what is existing.
Okay.
That will give you the new solution. So R1 that we find is 3.1260 and R2 is 2.3199. So the new solution, when you put in the put in the equation, that is the second equation that we have used, that is the C2, the equation having C2. This is the equation 2 we have used. Then put these values in that equation. Then we got it 17.2697. So that will replace the worst solution. That is the worst solution was existing here. So that has been replaced with 2.20 and 1.90, and it is 17.2697. So we go on now. This is the worst solution we found, and the best solution remain what we initially generated, that remains as it is. Now we use the best solution and find two new solutions. Find the new solution, and the worst solution will be replaced. So this process continues till you get the best values. This is what the very simple logic. Only thing is that we have to what is the variation that was existing in the values in the population pool of X1 and X2. Only that variation we play and generate new solutions, replace the worst solution, and this process continues till you get the best solution. Uh, so this is the way you do. Now this SOPT, to test what should be the values of C1 and C2. In fact, C2 is a half of C1. So what should be the values? A lot of experiments have been conducted. Experiments have been conducted based on the unconstrained available unconstrained problems. In fact, we considered 25 problems, unconstrained problems available in the literature, for which the best solution or optimal solutions are known so far. So only those benchmark problems were used, and the value of C1 is changed from 1 to 3. Value of C1 is changed, and the population pool, population size of the population was taken 50 for all the problems. So 25, I shall show you the problems later on. So 25 problems have been taken, and then we found that uh, when we take the value of 1.5, C1 value equal to 1.5, most all the 25 problems are getting solved, or getting solved means giving the non-optimal solution. That is the getting solved. We get the non-optimal solution for all the 25 problems. Whereas when you take C1 equal to 1, for many problems you did not get the optimal solution. When you take C1 equal to 2, you did not get a solution for many problems. So then doing so, we found that C1 should be equal to 1.5. Then you see the benchmark problem that we have that we used. In this case, these are the benchmark problems, 25 benchmark problems. So all these problems, here we mean the benchmark problem. T means the dimensions. You have X1 and X2 here. This is the dimension for this problem. That is the EOSM problem. And UN means U means unimodal. There is only one mode for the solution. M means multimodal, and N means non-separable. Where S will be given, it is a separable problem. So different characteristics of the problems are existing for all these 25 problems, and the best solution, the range is given for the values of X1 and X2, and the solutions are known for such type of problems. So then you see the results that we, with 25 problems, the results that we got, these are the actual optimum values for such type of problems given. Then these problems were solved by simple optimization technique, SOPT, as well as particle swarm optimization and teaching learning based algorithm. So for comparison purpose, we used two other algorithms, and the problem shall be solved. Now you see, SOPT gives optimal solution for 21 problems, where PSO gives the best solution for 15 problems, and TLBO gives best solution for 20 problems. Now the results of PSO have been taken from the literature, that is Karavaga et al. So that has been, a comparison has been made. Similarly, look at the computation time taken in seconds by for all these 25 problems using PSO, SOPT, and TLBO. Okay, this is the computation time that is taken. Um, Now, what we observe in these results, it is found that SOPT algorithm is able to reach best known solutions for 21 problems, while TLBO reached to best known solution for 20 problems only, where PSO, particle swarm optimization, gives the solution for 15 problems. Functions, that is Ewson function and Matthias function, which are unimodal with flat surfaces, are getting solved by all the algorithms. But the functions like Rasterising, Grivank, Schweffel, Ackley, which are having large dimension and highly multimodal, multiple modes. There is not only one peak, multi-peaks, multimodal. These are difficult to solve by any method. However, TLBO algorithm claims to solve Rosenbrock function or giving the best known solution, optimal solution for Rosenbrock problem, which was not solved by any other algorithm, whether SOPT or PSO. By other algorithms, we could not get the best solution. But TLBO claims they have solved Rosenbrock problem and got the solution. Now, uh, as far as the um, as far as the computation time is concerned, it is found that TLBO performs well and reaches to 13 solutions at less time compared to SOPT. For 13 problems, TLBO takes less time than SOPT. But SOPT takes less time compared to TLBO in solving 12 problems. And SOPT reaches solutions to 14 problems in less time against the PSO, which performs better in 7 problems in terms of computation time. So, if you compare the computation time also, SOPT takes comparable less time. So, it is a computing algorithm which can be used for solving many engineering problems. Now, what is important is that the algorithm is very simple and if one parameter is there and you need not to do anything. All the generating the random numbers, everything is available in the MATLAB. Coding will be very easy. So, lot of advantages are there. Now, let us solve one function, that is the ESM function. This is the function given here, and now it is a flat function, and the best value is known, that is the fx will be -1 when x1 equal to pi and x2 equal to pi. The solution is known. Now let us solve using the SOPT. So this is the code for SOPT algorithm that was developed. Now any algorithm, if you solve using any algorithm, you must give a convergence score. Convergence score means it gives the changes, how the changes have been taken place in fx as the iteration proceeds, as the number of iterations proceeds, how the fx value is going to be changed. Now, I've told you that for this problem, use some function, the best value is -1, fx value is -1, and the so get the here we got the solution, that is x1 is 3.14, x2 is 3.14 pi, x1 equal to pi, x2 equal to pi, and fx equal to -1. Okay. So this is the conversion convergence curve that I have already shown you. Now, now I think teaching learning based algorithm will be covered by some other experts. So I am not going to the details of the teaching learning based algorithm. But while solving some of the problems, I shall demonstrate teaching learning based algorithm. But I'm not covering that one. Let us have a particle swarm optimization, how it works. The particle swarm optimization is nothing but it works based on the behavior of the birds. So you just imagine the birds are sitting on a trunk of tree, and they find a food source at the ground. What they do, all the birds will will rush to the food source, and they exchange the information among themselves. So when a bird is sitting on the tree, then we can imagine what is you can define their position. The position can be defined in three coordinates, that is x1, x2, x3, or x, y, z coordinate. So suppose I have three variables, then this coordinate x1, x2, x3, or x, y, z, this is the coordinate that I can define a bar. Then in each coordinate or each variable we have so that we call three dimension. Under three dimension, I can give the values, that is the position value. For x1, what is the value? For x2 x2, what is the value? x3, what is the value? Then when the race rush to the food source, this position will be changed, and they change the velocity. So velocity can be in the x1 direction or x2 direction and the x3 direction. All the three direction velocities will be changed. So a particle will be defined by the dimension, a position, and a velocity. Right. So the dimension depends on the number of variables that you are having. Suppose you have three variables, then three dimension, then you have a five variable, then five dimension. So under each dimension, a particle is defined its position, the values occupied under each coordinate or the dimension. Then under each dimension there is a velocity. Now what they exchange the information when reach at the food source, these position values and the velocity values go on changing or being exchanged. So a bird can have its best position values. Position values are nothing but the solution. These are the values of x1, x2, x3, all these are the solutions. Now a bird can have the best position values, its own, as well as a swarm, number of birds you have generated or a population you have created. Among these birds, you may have a best position values. So the position value that a bird has achieved so far, the best position value a bird has or a particle has achieved so far, that is known as the personal best, and the overall in that group, what is the best position value that we have got? That is known as the global best values. So we just exchange the information between this global best and the personal best, and find out find the change the velocity values and the position values from time to time. So where t here represents the iteration number. So in the next iteration, the velocity of um, particle particle I in jth dimension will be given by this equation. If here W is known as a weighting factor, then two parameters are used, that is the C1 and C2, and R1 and R2 are two random numbers between 0 to 1. C1 and C2 are known as uh, cognitive and social parameters. The values maybe 2. Of course, it depends from problem to problem, but normally the value is 2. And R1 and R2 are the random numbers between 0 to 1. And Pij is the personal best values, and Gij is the global best values. Then once you change the velocity values, then you change the position values. The position values are the solutions. So to do this, what we do, we generate randomly generate the particles, randomly generate the position values and the velocity values for each particle. Then in the next iteration, we evaluate the initial iteration, we evaluate the fx values and find out the personal best and the global best. Then in the next iteration, position values are changed. Once the velocity values are changed for each particle, the velocity is being changed and the position values will be changed. And the W, which is known as the inertia weight used in this equation, that also go on changing from iteration to iteration. So this process continues till you get the best solution. This is one example given. Again, use the Rasterising function. We get the Rasterising function. Take the C1 and C2 equal to 2, and the velocities are generated between two limits, that is between 0 to 1, 0 to 1, and similarly the position values are generated between 0 to 1. Then you generate the initial solution x1 and x2 values, then the velocity values v1 and v2, and put in the objective function value, and get the objective function values. So initially we generate initial population, then go on changing using these equations, and till we get the best solution, we will find out. So this is the MATLAB function that we can solve for particle swarm optimization. As I told you, for the Rasterising function, x1 will be equal to 0, x2 will be equal to 0, and fx will be equal to 0. That is the optimum value. So after 20 iteration, we found x1 equal to 0, x2 equal to 0, and it is fx value equal to 0. Now come to one example where we have used these optimization problems or algorithms. Now it is an ultrasonic machining process. As you know, all of you know what is the ultrasonic machining process. That is in ultrasonic machining process, high frequency electrical signal is fed to the transducer, then it produces mechanical vibration in the ultrasonic range. Then the tool vibrates in the range of ultrasonic. Then there will be abrasive slurry that is the mixture of silicon carbide, boron carbide, alumina. Then microchipping will take place from the workpiece till you get the best shape on the workpiece. Now here you see there are 5 decision variables that affects the material removal rate in ultrasonic machining processes. Now that is the maximum displacement of vibrating tool from its mean position, that is AB, that is in mm, frequency of the vibrating tool FB, that is in hertz, and mean diameter of the abrasive grain, that is the DM in mm, concentration of abrasive particles by volume in slurry, that is CAB, and the static feed force applied to the tool, that is FA. Now this can be solved is say your function will be maximize material removal rate. This formula can be this is a formula which is basically an analytical formula. Okay, this formula is found out. This is given in reference 17, where this formula is given. Then you will give a constant to the surface roughness. So surface roughness constant is given. Now all the values, all the variables AB, FB, DM, CAB, FS, these will be within these limits. Okay, the limits. Now such type of problems can be solved, and the constants that we can have, that is the AT should be cross-sectional area of cutting tool, AT will be taken 20 mm square. So these are the constant, that is constants that will be used in this problem. Then your surface roughness, what is given, the surface roughness equation, surface roughness should be should not exceed 0.8 micrometer, and indentation ratio lambda is 0.246. So these are the parameters that will be given. Now we solve using many algorithms. Now if we see the calculate the material removal rate and array, which should be array will be less than equal to 0.8. Now you see only TLBO and SOPT, they could achieve the MRR around 4, whereas PSO and HS they have not achieved MRR around 4, but TLBO and SOPT achieved around 4. However, SOPT has improved a little bit, 4.0064, and if you compare RA value, which is less than equal to 0.8, in TLBO it is 0.799, and in SOPT it is exactly 0.8, and in PSO it was 0.792. So many so such type of problem can be solved, and this is the convergence score for using SOPT. Then another type of problem that has been solved, again this example is from again 17. This is the wire electrical discharge machining process. In wire electrical discharge machining process, you know there is a wire which moves around the workpiece, and a spark is generated between the conductive wire and the workpiece, and during the sparking process metal is removed from the workpiece, and both the wire and the workpiece, they are dipped in the deionized water. Now what are the important decision variables or the parameters that we are having? That is the pulse on time, pulse off time, peak current, and servo feed setting. So these are the 4 parameters have been taken, and these are taken as x1, x2, x3, x4 variables. T on is the pulse on time, T off is the pulse off time, IP is the peak current or the discharge current, F is the servo feed setting. Now, equation for maximizing cutting velocity, cutting speed, maximizing the cutting speed, that has been developed, and this is an empirical relation which has been developed through experimentation. We have conducted the experiment and developed this regression equation. This is not a theoretical or analytical solution. Similarly, for the surface roughness also, um, the equation has been developed through empirical modeling. So range of the decision variables have been taken, T on, T off, IP and F. This range of decision variable is taken and it has been solved using four types of algorithms: PSO, HS, TLPU and SOPT. Now, if you look at the machining speed, VM, we see that SOPT has given good solution, um, comparable solution with TLBO and HS and PSO. It got 1.422, and RA, that is the surface roughness, is less than 2. What is the constant that we have taken? That we got 1.999 in SOPT, where in TLBO this we got it 2.019. In fact, TLBO violates the constraints, whereas the SOPT doesn't violate the constant. That's why it is a so we say that SOPT gives a good reasonable solution to such type of problems. We shall be discussing some more problems and also the constraints, how we handle the constraints and the HS algorithms, then the multi-objective functions. So let us have some break and we shall be discussing after say, around 12 o'clock. Hello?
Yes, sir.
Around 12 o'clock again we begin.
Okay, sure, sir. No problem.
Do you have any questions right now? If any questions, if you are having any question, please ask me. If you are free to ask any question, don't worry. Hello? Okay, okay, again we will meet at 12 o'clock, right?
Okay, sure, sir. Sure, sir.
Okay, okay.